Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Imagine catching data issues before they snowball into bigger problems. That's what Datafold's new monitors do. With automatic monitoring for cross-database data diffs, schema changes, key metrics, and custom data tests, you can catch discrepancies and anomalies in real time right at the source. Whether it's maintaining data integrity or preventing costly mistakes, Datafold monitors give you the visibility and control you need to keep your entire data stack running smoothly. Want to stop issues before they hit production? Learn more at dataengineeringpodcast.com/datafold today. Your host is Tobias Macy, and today I'm interviewing Weston Pace about the Lance file and table format for column-oriented vector storage. So, Weston, can you start by introducing yourself?
Hi, nice to meet you. Yeah, so I'm Weston Pace. I'm a software engineer at LanceDB. I'm on the PMC for Arrow and Substrate. I've been doing data engineering and open source for a little while now, but only about the last 5 years.
And do you remember how you first got started working in data?
Yeah, so it's kind of a funny story that when I was in college, we had to pick what courses we wanted for our senior year. And there's just this big syllabus of all these interesting computer science courses. And I remember saying very distinctly at the time, was like, I don't know what I will take. The only thing I know is I'm not taking databases. Data seems like such a solved problem. This was back in 2010. And so after many years of app development and kind of unrelated things, I found myself working at a company that did test and measurement. And they built these really expensive, precise measurement devices. And then they output a CSV file and told the customers kind of have fun from there. And so we were working to build a much better data solution. And so then I ended up having to figure out, okay, well, what is a data solution? What is a data lake? What are all these data things people are talking about? Started working with PyArrow a lot and then ended up working for Ursa Computing, kind of doing PyArrow and Arrow C++ maintenance full time.
It's interesting that you eschewed the database courses in your academic career, and now here you are writing the lowest level aspect of a database.
yeah. It's like not only am I working on a data lake or something like that, I'm working on data storage and file formats. And again, something that I thought was surely solved by this point. But,
it's solved to a certain extent. There are always other solutions to it, just like everything in software engineering. The answer is always it depends.
Yeah, that's a really good way to look at it. Is like there are great solutions out there, and then there's always just a further niche, a further corner to explore. And as solutions get more and more advanced, you have to start looking into those things.
Absolutely. And so, to that end, can you start by giving an overview about what Lance is and some of the story behind how it got started and how you got involved with it?
Sure. So Lei and Chung are co-founders. Started it. This was before about 6 months to a year before I'd really gotten involved. Chung was working at Tupi and Lei was working at Cruise at the time. So you're both working with a lot of kind of multimedia data. They need to solve these vector search problems and just other kinds of search problems. And even outside of search, just working with image data and video data, there were not a lot of great data solutions. And they were kind of building things internally, but also realizing like there's just a big hole here in the database world of a good solid solution for working with this data. And so they decided to start a company. And so now Lance is we've kind of been focused on, we do a lot of vector search type tasks. That's where we got our start. And now there's a big focus on just multimedia data management in general. So kind of a database that can handle vector embeddings, it can handle compressed images, it can handle raw images or video, it can handle all your basic scalar TPCH style data as well. So trying to find something that handles the problems that a lot of AI engineers are kind of running headfirst into now.
And as you were mentioning, vector search, vector storage, those are, again, solved problems if you look at it in a certain way, where there are vector databases, there are databases that have vector indexes, some of them have support for multimedia storage, others are focused on being able to store embedding matrices and text documents. And I'm curious, what are the core problems that Lance is designed to solve that aren't addressed by all of those other solutions?
Yeah, that's a good question. So there are, as you pointed out, sort of special purpose tools and libraries for a lot of the different problems that need to be solved. And so vector index is a good place to start. So like vector search, we have Face is the vector search library essentially, and then Pinecone and a number of others have built on top of that or built their own sort of specialized vector search. And initially, they were all in memory, very much just focused on just being this thin index that you can attach to your data engineering solution. The problem is, uh, it's not data engineers that are running into these problems. It's machine kind of ML engineers, ML scientists, people who are trying to build models. They don't want to build a giant data engineering customized solution. They're looking for a database. And so when you have something like an in-memory vector index that maybe they threw in, oh, you can also attach a metadata object to each vector. It's very different than having a database where one of your columns is a vector embedding. You can create an index on that, or you can do all your normal database stuff on your other columns. You can, create an index on your genres column and use that for filtering. Or a very common solution that I think people run into is things like, okay, I want to load all the images that match this filter because I need to do some kind of training on that small data set. And then further, maybe I only want 5% of those matches and I want them in random order. Or it'll be, okay, I start with a bunch of images and now I'm going to go and I'm going to calculate some embedding. Oh, wait, now I want a slightly different embedding. Oh, wait, now I want maybe a different embedding. But go ahead and store all of these because I'm not sure which one I want to use. Maybe I won't actually know until query time. Maybe I want to use all three and kind of pick the best. And so these are all things that kind of having an all in one database that handles all of these different use cases is more convenient than having a fairly complex custom built data engineering solution that's using a bunch of different tools.
And it's probably also worth calling out the differentiation between LanceDB, which is the I just have an in process or a serverless database engine for doing all of this vector storage, from the Lance file and table format, which is the underlying piece that powers LanceDB, but is also usable independently of that LanceDB interface. And I'm curious if you can maybe give some thought as to what is in scope for the Lance file and table format, and what are the pieces that you are explicitly keeping out of scope for that because that is the domain of the Lance DB or whatever other client is interfacing with the file store.
Yeah, that is a good question, and one we're still kind of clarifying and better explaining because we do have these different layers, and we want to make sure the distinction of what belongs in each one. So we have a file format at the lowest level, which is a storage format like Parquet or kind of like the Arrow IPC format, or just some way you can store tabular data. And when we have a Lance table format, which again is going to be very similar to some of the other table formats. So it's like Iceberg or Delta Lake, it's solving the same problems there. And then on top of that, LanceDB is more of the application view. It provides the user with an interface that they're kind of expecting from a database. So you connect to it, you insert things, you perform searches, and that's about it. It hides a lot of the complexity of really the lower level table format and file format. So Lance, I think the project in Python is PyLance, is going to be much lower level. It tends to be more flexible. You can do more things with it. And so when you're building certain integrations, sometimes you have to drop into those lower level libraries. Like if you want to do a complex multi-process bulk ingestion or something like that. Whereas LanceDB is more of okay, here's a straightforward API that doesn't take long to learn, ingest a bunch of data, do some vector searches on it.
You mentioned Parquet as the analogous file format, which has been very popular for data engineering, especially for data lakes and lakehouse architectures. In the README, it mentions that it's very straightforward to convert from Parquet to Lance, and that there are some fairly substantial speed benefits that you get I'm wondering if you can talk to some of the motivation behind that compatibility support and some of the cases where maybe you want to keep your data in Parquet for whatever use case, and despite the fact that you're going to get speed improvements from using Lance.
Yeah, I like Parquet. Parquet has done a surprising number of things right, and so it's a great library. Actually, that's kind of how I met Chung and Lei. So Chung and Lei were working on the original version of Lance, which was at that time in C++, and they were using Arrow C++ and PyArrow and PyArrow datasets. And I was maintaining PyArrow and PyArrow datasets at the time. And they came to me and they said, I'm just trying to pull one vector, one row from my file, and it's really slow. And I said, well, yes. And they said, can I make it fast? And it's sort of like, well, there are quite a few things we can do in the library to make this faster. It hasn't been a priority yet. At some point, you're going to run into some limitations within the file format itself. And I think we've learned since then that both those things continue to be true, which is people that build Parquet libraries aren't often thinking about random access. And so even in cases where the format could handle random access better, the library doesn't have the right APIs. It's not being as efficient as it could be. And then when you get down to the format with Parquet, there's certain things that just make working with this data in Parquet tricky and not quite as optimal as it could be. And I talk about random access a lot when I'm talking about Lance. And that's because two of our main use cases in the multimedia AI data world boiled down to random access. So any kind of search problem is usually you're searching against something that you can't turn into a nice primary clustered timestamp style index where you can just sort of shard your data files and sort by that column. So like searching vector data, there is no nice sort algorithm for vector data. So you can do like Z-order or Hilbert curves or something like that, but it's not really going to solve the problem. And so when you do a vector search, you search this very small index file and it tells you which rows you want. And now you have to go get those rows, and that's random access at that point, more or less. And the other is when people are doing training, they want their data in random order. And so they need to have some kind of efficient random access. And with Parquet, you can really cheat. And I'm rambling a little bit here, but if you'll allow me, especially with cloud storage and with Parquet, you can get away without having random access a lot of times when you're dealing with TPCH style scalar data, so numbers and small strings. Because if you have, maybe a billion rows, then you have, like if it's a 64-bit integer, less than 8 gigabytes of data. And cloud storage is going to give you, 4 or 5 gigabytes per second easily. And so you can search that entire column and just do random access within 2 seconds by loading the whole column and throwing away what you don't need. And you can do much better than that with Parquet. You don't have to pull down the whole column. You pull down the pages you need. The read amplification doesn't have to be too bad. But once those columns are vector indices, you hit this interesting sort of sweet spot where a vector index, like a sample one, might be 4 kilobytes per vector. Now, suddenly, if you want to pull down a billion vectors, you're talking about 4 terabytes of data. That's not something you want to search through exhaustively. And even when you talk about like page level random access, if you're saying, well, I can get you to within 10,000 rows, we're still talking about now 10 megabytes versus 4 kilobytes. That's way too much. We need a much finer resolution to random access. But at the same time, vectors are not nearly so big that you can get away with just using like a blob storage or something, just saying, this vector is a blob. Every single one gets its own file, or I'm going to use some special format, and I'm going to perform an IO operation per vector for all of my columnar tasks. That doesn't work either. So you need columnar storage, but you also need good support for random access. And so that's sort of the origins of the Lance file format and how we started moving away from Parquet.
In that random access question as well, as you noted, column-oriented formats are best for aggregates or scans of a column, but if you're doing random access of a vector, the chance is that you also want to get one of the attributes of that same row in order to be able to understand what is this vector even telling me, because it's just a bunch of floating point numbers in a matrix, but what I actually want is the text that it represents or the image that it represents. And so from that perspective, I'm wondering, what are some of the ways that you're addressing that row attribute access while still being able to take advantage of the columnar compression that you get?
That's a good question. And what we've got today, and that works pretty well, is we stick with columnar, but for each column, we can grab the values in really like one IO operation. If it's like a string or some kind of variable size column, you need to. And so then the math becomes pretty straightforward. If you say you're taking 5 columns and you need 10 random rows, you're going to end up with like 50 to 100 IO operations. And you said, well, if I stored those in row-based storage, I could drop that down, 5 times less than what I had otherwise. And that's true, but we haven't usually needed to go that far. And in the cases where we do need to go that far, something we're working on right now is the idea of, it's called basically the packed struct encoding. And it's saying, take these 3 columns or maybe these 4 columns, and I always need to access all of these or none of these. And so we'll go ahead and just pack them into one column. And so you end up with kind of a dial that you can turn. You can turn it all the way to 0, which means every field is its own column. And you can turn it all the way to 1, which means that you now have a row major format. And you can turn it anywhere in between. So you can kind of fine tune to what your patterns are. So like we have, some customers we found where they have a very, very consistent query pattern. I'm always going to want these 5 columns, and I'm going to be querying thousands of times per second. Well, then it makes sense to go ahead and pack those columns together. But most of our customers are in sort of the, okay, I don't have thousands per second queries. I really need to be able to do a lot of data exploration and filtering and things like that. So there are times where I just want individual column access. I just need random access to not be too slow when it comes time for it. And what we found is columnar is not too bad for that. It works in most of those cases. And when it's not, you just turn the dial.
As far as data modeling, the most notable addition that Lance adds over and above Parquet or other file formats is a native vector representation and vector indexing. I'm wondering if there are any other features or constraints that engineers need to be thinking about when they're modeling their data embeddings or modeling their overarching data, where maybe they use Lance for all of the vectors and the mapping of what the vector is representing, and maybe they use Parquet for all of their standard tabular SQL data, or any variation along that axis.
Well, so luckily the answer is things work together well these days. So I've really loved the work of the Arrow project. I worked with Arrow for quite a while, and one of our other kind of core file table developers, Will, is also comes from having worked on Arrow for a while. Lance is fully interoperable with the Arrow type system. So all Arrow types can be stored in Lance and retrieved that way, which means we more or less have full interoperability with Parquet. So even our vectors, if you wanted to convert them into Arrow and then to Parquet somewhere else, you can do that with the fixed size list data type. One thing we found as we started using this fixed size list data type a lot more is that there were a number of libraries that had just gaps for fixed size lists because they added it, but it was kind of an afterthought. And so we've been, not so much anymore, but it's like a year ago, we had to fix a number of small things where fixed size list just wasn't supported. There was no equality function for it, or there was no hash function for it, or you couldn't use it in this spot. And so we helped round out that support. So for the most part, you don't have to worry. It's PyArrow types, everything kind of interoperates. There are like minor thoughts when data modeling. It's nice if your vector embedding is a multiple of 16, because then that makes the SIMD algorithms that we run on it work nicely. But that generally hasn't been a problem. Every one that people have come up with works well. Yeah, so we try to be flexible and robust so that your data modeling decisions shouldn't have major impacts on your performance.
One of the key considerations around data modeling in the context of vectors that I've seen for some of the other vector engines is that depending on how they approach the implementation, there may be a hard limit on the maximum number of dimensions that any one vector can have for various reasons, either because of purpose of space constraint or because of the computational complexity of maintaining the indices, et cetera. And I'm wondering, where do you fall on that side, both for the case of Lance, the file and table format, and Lance, the database interface?
It's a trade-off. Smaller is always better for performance. So if you're able to do like SIFT vectors are like 128 8-bit vectors, great for performance. You can train a index on SIFT vectors very quickly and easily. We see a lot more often now, it's like 1024 4-byte vectors. Those are just going to be a little slower because there's more data to process. And it's a trade-off. You get better accuracy versus better performance. As far as limits go, once you hit 1 megabyte per vector, I would say that things are just going to be really slow, but go for it. We don't actually have a hard cap beyond, cannot go larger than 2 gigabytes per vector. But I think you're solving a different problem by the time you get there. And you might actually be able to get away with it. No, there's probably, I think it's a 32-bit size in arrow for the dimension of the vector. But otherwise, I don't think we have any caps in there. Lance as a file format and table format it doesn't stop you from shooting yourself in the foot maybe as often as it could. LanceDB will try a little harder, but I don't think we've run into needing to add a vector cap yet. Yeah, a vector index itself is interesting too, because it's basically a lossy compressed version of the vectors that you pass in. And so you end up with just this hierarchy of compression, which is like your original document or image or whatever. Conceivably, if you're able to compare those, you would get the best accuracy. But it's just too much data to compare in a meaningful way. So you have these embeddings, which are effectively lossy compression of the images. And then you put them in a vector index, which just kind of compresses them even further. And then you get to play this game of how much compression is too much compression before my recall starts to fall off a cliff.
For children of the 90s, how many times can you copy that CD before you stop being able to hear it anymore?
Yeah, exactly.
And in terms of the modeling from the file size and chunking perspective, what are the considerations that people need to be aware of when they're thinking about, I'm going to be using this in some sort of cloud store, I'm going to be doing scans and searches, whether it's from LanceDB, or I know that the Trino engine is working on adding support for Lance, and just some of the ways to think about the balance of IO performance against the network retrieval times and the searchability of those chunks, where you don't want to have too many small files, but you also don't want to have everything in one big file, and just some of the rules of thumb or the heuristics to go with for figuring out how to actually segment those files.
So I used to work with Pyro datasets and Parquet, and there would be a lot of those sorts of configuration things. One of our goals with Lance was really to get rid of those as much as possible, because we found when you add these wide data types, it either becomes hard to figure out what the right setting is, or just downright impossible. There is no good setting. So with Lance, we got rid of row groups, which I told my friend at the time, if getting rid of row groups is like the only thing I do in my life, then I will consider it a success. So hopefully that can eventually propagate back to Parquet and other file formats. And so what's left is we need page size. How much data do you buffer before you write to the disk? But 8 megabytes is works well for everything. That's big enough that you're going to have good S3 performance, and it's not so big that you use up too much memory. So 8 megabytes per column is usually a reasonable amount of memory for a writer to use. So I think the only one that we might play with still is how many rows you have per file. And I think the minimum is what we use today, which is 1 million. You really shouldn't be going below 1 million because then some of your columns are going to be just too short. There might be some cases where you want to go above 1 million, but we found for pretty much all of our customers and use cases, the defaults work fine. So that I was very happy to be able to achieve.
And now digging into the table format, you mentioned that it's analogous to the iceberg table format that's become very popular for these cloud data lakehouses. And I'm curious if you can talk to some of the design considerations around the Lance table format, juxtapose it with maybe iceberg or hoodie or delta, whichever table format you're most well versed in, and some of the ways that they are disjoint and the ways that they can interoperate.
So those formats we would like to be able to support. There's sort of two questions. There's like one is being able at some point to do vector search on those existing formats. Another is being able to get those formats to use Lance files. So doing vector search on those formats, there was some interesting research done recently by a friend of mine, Tony. He kind of built this system called Rotnest, where he was able to build vector indexes against Parquet and search iceberg data lakes. And there's a few challenges that you run into. One is that Parquet doesn't do great on that random access problem. Two is that the table formats don't really have a standard for where you put those index files, and the readers aren't designed to look for them. And then three is one of the challenges that we inspired us to do our own table format is this idea of the row ID and being able to, because in your index, what you essentially have is usually a column or columns of searchable stuff. And then you have a column of row IDs. And so you search the small searchable stuff to find your matches, and it tells you what your row IDs are. The problem is you can use what we call row addresses, which is like the 5th file and the 17th row. That is something you can use with Iceberg. But that address is going to change when you run compaction. It's going to change when you delete rows or update a row. And you need to then be able to reflect that change somehow in your index. So either you're updating your index when you're doing compaction, which is how the Lance table format works, although we're trying to move away to something a little bit more sophisticated where you have kind of this primary index structure, which allows you to resolve those addresses from IDs. And so that's one of the challenges. And then as far as using Lance within Iceberg goes, it's something we would definitely encourage. It's not something we're actively working on right now, but I don't know any reason that wouldn't work. So I think Iceberg does have some placeholders in there for different storage formats. And again, you would run into, but I think you could solve some of these challenges where like libraries just aren't written with random access in mind. Like when we built our table format, we thought, oh, we do have this random access. So then we looked at an operation like an upsert operation. And what you're doing there is you're taking a table of new data and all your existing data, and you're kind of doing this join to figure out which rows you're replacing and which rows you're inserting new rows. And if that join is happening on a column that you have an index for and you have random access, then there's actually ways you can do that join more efficiently. So those types of tricks aren't necessarily going to be built in yet, but I think they could eventually reach it and take advantage of those as well. So I think we would like to see more integration there someday. I don't know that we're 100% ready yet or have a ton of time to work on it yet, but that's something that we always kind of keep in the back of our mind of making sure that we don't want to completely alienate those formats and that we're able to integrate with them. And also, one thing we want to do a lot with the Lance file format and Lance table format both is put these out there as examples of saying, hey, here are ways that you can support these operations. You know, if you're going to do an update to some of these existing formats, take a look at what we've done and see if you can integrate some of those features, because that would make it much easier for us to support those kinds of data in the future.
On the point of indexing, I know that in the context of AI engineering, where you're building some sort of a RAG system and you have an embedding model, anytime you change that embedding model, you have to completely rebuild the entire data set because the embeddings are no longer compatible. I also know that there are other cases where you can't necessarily incrementally update an index and instead need to completely rebuild it. And I'm curious how you're starting to think about that problem space in the context of Lance as far as how to allow for evolution of schema, maybe have some means of compatibility or updating of existing embeddings so that you don't have to rewrite all data everywhere. Just some of the challenges in that space.
Yeah, I'm glad you asked because that was thinking about Iceberg and Delta Lake. One of the biggest differences with the Lance DB format is we absolutely needed to be able to add a column without rewriting existing data. So if you think a lot of data lake models, you'll have this feature pipeline, which is sort of you start with some ingestion of raw data, you run through your pipeline, you add some different columns to it, and it writes out your data set. And then in that sort of environment, you add a new column. A lot of times what will happen is they'll just rerun the whole pipeline, rewrite the whole data set. It's 100 gigabytes of data, who cares? When you have already an embedding vector and maybe a billion rows, you've got in that embedding column now 4 gigabytes of data. 4 terabytes of data. And so if you want to add, what we'll see a lot of people want to add a second embedding. They don't want to drop the first embedding because they want to be able to do compare and contrast and that sort of thing. Well, if adding a column requires rewriting 4 terabytes of data, in addition to the 4 terabytes of data you already have to write, then it's just too expensive. So the Lance table format, our schema evolution, essentially what we do is we support multiple files per fragment where each file is adding different columns, which is something that Iceberg and Delta don't have yet. And that lets us to do we can add columns essentially for free. You have to write the new column, but you don't have to rewrite any existing data.
I can definitely see how that would be very valuable, like you said, for compare and contrast and experimentation, but also for purposes of when you have a situation where you say, this embedding model is better than the one I had before. Now I need to go and regenerate all of these embeddings, but I already have the actual core data that I'm representing in the Lance files, so I don't have to rewrite all of those. I just have to update the embeddings. So that's definitely a very useful approach to that. And I can also see it being useful just from a generalized schema evolution perspective of, hey, I want to add this new column and I need to backfill the default values, which is something that you might do in a typical application database, but that's because you're only dealing with hundreds, maybe thousands or low millions of rows, where you're dealing with, megabytes to low gigabytes.
Yeah. And like you say, we've had customers that have come to us and said, I don't care about vector search, but the fact that you can add new columns into that schema evolution cheaply, and the fact that I can do my training against this data, that's all I need. So that's one of the main use cases that we want to keep supporting.
And also, I can imagine that even if you're not going to completely replace an embedding model, maybe you have a different vector representation that you need for a different use case. Maybe it's a lower dimensionality or a higher dimensionality vector where you need either greater accuracy or greater speed, but you also still want to have the default embedding for a different application. It supports those use cases as well.
Yeah, there's a few use cases. One, like you said, where you're making a trade-off between two embedding columns. There's also, like, you will have sometimes when we're dealing with string, for example, we might create an embedding, which is like a semantic embedding to allow semantic search. But we also want the original string column itself because we want to be able to do full text search. And then we need to write a full text index, which has its own copy of the data. And so having those all there so that you can use, sometimes you even want to use both of them. And that can be true even for semantic search. Sometimes you'll have two semantic models and you can search with both semantic models and then re-rank the results using some of these cool re-ranking algorithms. So we've had one of our biggest sort of customers in terms of like how fast they hit the system has several different embedding models. And that was one of the key features they liked.
And in that context of building AI applications or retrieval augmented generation systems, it also brings up the question of latency, because the LLMs on their own add enough latency to the system. So you want to try and speed up all the other pieces so that the end user experience is as fast as possible. And I'm curious as to some of the ways that you're thinking about the speed of Lance as a file format and table format and some of the different operational environments that will benefit that latency trade-off where maybe you don't want it all running in S3 because then everything is a network hop. Maybe you want it all running on disk somewhere, and just some of the different deployment considerations about how and where to store that data, particularly, and then also being able to age out data where this data is old, I still want access to it, but that goes in S3. This other data here is running on SSDs, so I can get faster latency.
Yeah, one of the biggest challenges that we faced initially, and took us a while to gain confidence that we were overcoming this, and we're kind of happy we are now, is we came out with a vector search product that was built against storage. And at the time, all of the vector search products were built against memory. And so we had to prove, can I still get latency that matches Pinecone running against memory, or my custom face thing that's running against memory? And we're not magical. So against pure S3, you're going to have limitations. But what we're seeing now is you have S3 Express popping up. You have iMjuice and Weka, these sort of S3 caching layers that are popping up. And then in our enterprise deployments, we actually have our own sort of caching solution that'll do NVMe cache on top of S3. And once you get there, then two things happen. Is one, you're absolutely fast enough, you can kind of match those latencies. Your IO is now kind of on par with your compute. Vector index searches are actually pretty compute expensive as well. And so we reached the point where IO is not necessarily the bottleneck for latency anymore. And two is you hit the point where, again, as I've been kind of saying, a lot of those assumptions that were baked into Parquet and cloud storage of, oh, well, it's cheaper to pull down the whole column than it is to do some random access and grab the bits I need. Those start to fall apart as well once you have these caching layers and these really fast IO layers in place. So latency is critical in a search application, but by choosing just storage in general, we haven't really written it off. And what we've seen now that we really like to see is Pinecone has said, oh, you know what, maybe serverless and running against storage as the final backend is not such a bad idea. And so they're trying to adopt our model as well. You have TurboPuffer popping up, which is another vector search company that's also built against cloud storage with caching layers. And so we're kind of feeling pretty confident that that is the way things are moving going forwards, which is you can build your product against cloud storage and you're not going to get great latency, but make everything work. And then these caching layers can add the latency and get you competitive with something that's running just in memory.
Another interesting aspect of the table specification is that it has built-in specification for feature flags to enable various elements of experimentation. And I know that you also said that you have some extensibility mechanisms in the file format as well. I'm wondering if you can talk to some of the decision process for adding that feature flagging, some of the use cases that it enables, and how it has aided in enabling some of that experimentation and rapid development for a format that is targeting such a fast-moving ecosystem.
And we have had to make sure that we can evolve quickly. And at the moment, we are open source. We have the benefit of, we're not multi-vendor open source at the moment, so we can kind of move quickly. And so that's been helpful. We've evolved quite a bit since our original implementation. So we were able to prototype with the feature flags some things like a stable row ID. I kind of alluded to that before, but that was something that we were able to change, and just having a spot to mark, oh, I'm doing something a little differently here, make sure that you can support it has been great. Another one that I think I have to give Will credit for this one is one of the first things that you do when you connect to a LANS data set is you want to get the latest version. And so you have to, if it's stored in cloud storage, you have to do basically a list bucket command to get all the versions, and then you find the latest one. Well, turns out all those buckets return data in reverse alphabetical order. And so one of our flags that we just recently added is, hey, I'm going to start naming my versions at 999999999 and working downward instead of starting at 0 and working upward. And as a result, the latest version is always in the first. We don't have to page through the list bucket command, and we can find our latest version much quicker that way. But I think extensibility needs to be baked into everything. Like with the file format, we put in our pages you have to say, well, what encoding am I using to encode the data for this page? And what compression am I using? And I said, just make it a protobuf any object. And at the time, people said, well, that's now you're adding this extra layer of like decode, and you're putting in if checks, and it's going to slow things down because it's too much. Like the standard at the time was, oh, here's an enum, and if you want a new encoding, you change the spec to add support for new encoding, and you reserve yourself a new slot on the enum. And it's like, well, one of the nice things that we did in the file format is pages are always 8 megabytes large, which is, in the grand scheme of things, huge when you're looking at like rows and how much data you have. So there aren't that many pages in a Lance file. And that lets us be very flexible with our encoding. So now you can add, we're still trying to get the SDK out there and things like that for it, but we've got support for basically being able to add a new encoding without making any change to the code at all. You can just take a plugin, throw that on there, and now you have a new compression technique. And because what we're seeing is compression techniques, again, something that seemed relatively solved. Well, now people are talking about fast lanes and FSST and ALP and all these interesting compression techniques. And I think we start to see people looking at these LLMs, and now you suddenly start to have new domains and new compression techniques. Like people will say, oh, every row is a source code document because I'm building the next Copilot. And it's like, all right, well, maybe if we take advantage of that fact, we can build like a column-wide dictionary that knows all of the tokens in your source code. So like if and while and switch, and maybe that can help compression. I'm not actually an expert in designing these. Maybe this is way off base, but we wanted to be flexible for that kind of thing.
In terms of the engineering effort to build this format, build the table specification, and some of the design considerations that you've gone through as you have developed and evolved the formats, I'm curious if you can talk to some of the most challenging or most impactful decisions that you've made.
Yeah, so I talked a little bit a while ago about removing row groups. And for me, I think that was it was impactful. I felt that it could be done, but it also needed to be proved. And I needed to come up with a clever way of doing scheduling so that you can still get parallelism, even if you don't have row groups. And so the first solution I came up with was really bad. In terms of it was just way too complex. And it's actually still the one that's in use today. We're working on 2.1, which will kind of make it simpler. But there was like a good month, I think, where it was kind of like, can I really get this? You have these concepts of running out of memory because I read in too much IO. I didn't have enough back pressure. And then there's also deadlock of I read in the wrong IO and I can't use it. And I can't read in more IO because my buffer is full. And then performance of making sure all of this can run quickly enough. And so that was the biggest just engineering design challenge that I've had to go through in the last, I think, 6 months. Fortunately, it all worked out. So we have this nice 2 gigabyte IO buffer, and we apply back pressure when it fills up, and we were able to get the priority scheduling in there. And it will be all much, much simpler in a future version.
And as far as the access interface, we've touched on that a little bit, where it has support in PyArrow. You can use DuckDB for querying. I'm curious if you can talk to some of the other work that's happening in the ecosystem that you're building of different engines or interfaces or access methods for integrating Lance, particularly as people are investing more in this vector store and vector index space because of the rampant growth of AI and AI-based applications.
Yeah, we love kind of the decentralized database and the integrations that are popping up around that. Query engines, we use Data Fusion pretty extensively internally. And then we also use DuckDB. And so the way that we are able to get DuckDB to work is, I think, a good testament to the whole decentralized database concept. Is DuckDB is able to query PyArrow datasets. And so Lance is able to look like a PyArrow dataset. And so then we can feed that to DuckDB. So DuckDB never actually wrote a Lance integration. We didn't have to write a DuckDB integration. But because we look like a PyArrow dataset, DuckDB can query us. Although that does mean that DuckDB sends the pushdown filters in as PyArrow compute expressions. Well, PyArrow is able to serialize its compute expressions to substrate. And Data Fusion is able to parse substrate now into filter expressions. So we have DuckDB querying Lance because it thinks it's PyArrow, writing pushdown filters, which get turned into Substrate, which get turned into Data Fusion. And then we use Data Fusion to actually, well, then we search the Lance files. We give the data to Data Fusion, which actually applies the filters. And then we give it all back to DuckDB. And it all works. You can query Lance like an SQL database with that. It's very good for just like data exploration and playing around. Those integrations are fun. And having worked on the decentralized database concept for a while now, it's sort of fun to see these moments where it all comes together. And now we're also working with AI, and we're starting to see all these integrations that I, having been in data engineering, was just not really aware of. So you have things like Ray data and Torch data loaders, which any AI person will tell you, oh, of course, I use those all the time. And coming from Pyro Pandas world, I just wasn't all that aware of those concepts. So we have those integrations as well. Ray and Torch are popular. We've had a lot of community support actually around building up our Java integration so that we can have Spark against Lance. And then there's these various just very AI specific integrations like Olama and things like that, where from their perspective, they're not aware of anything data engineering related. Theirs is just a vector database, and Lance is one of the ones you can. So
as far as the applications of the Lance file and table format and some of the ways that you're seeing it applied, I'm wondering if you can talk to some of the most interesting or innovative or unexpected applications.
I think it's fun to see ways that vector storage can be useful. So like we've had people that use vector search for deduplication, duplicate elimination, which again, for maybe an ML person, it's kind of obvious that those two things are related. But for me, it's like, oh, those are the same problem. Oh, okay, I guess they are. I think most unique, I won't get political here and take sides on this, but someone did share that they used Lance to index the entire Project 2025 documentation so that it would become searchable for anyone that wanted to learn more about it. They could just do semantic search against it. And that was not something I expected to hear that we were getting used for. So it was definitely fit into the unique category. And then the other, I think, is just seeing people that are using this for, so one of the issues that we're working on right now is being able to store these really big blob type columns. And when I talk about blob here, I'm talking like 4 to 8 megabytes or more per value. So as people are putting in videos or something like that. And so we said, well, we really need these columns to be in their own category because we got to run compaction on them differently. Because if we take two 500,000 row files and compact them into a million row file, and one of those rows is 100 megabyte videos, then you're talking about something huge. And so the reason I bring this up as an interesting use is because the way we solve this is we're having Lance data set for all your data. And then if you have blob columns, there's a second Lance data set inside there that's just configured differently with different compaction thresholds. That's our blob data storage. So Lance itself uses Lance.
That's funny. It's turtles all the way down.
Yeah.
Going back to the extensibility point of both the table and file format, because of the fact that you're dealing with vectors and there's so much investment in that space, I know that HNSW is one of the more popular index formats for vectors. And I'm wondering, what are some of the ways that you're thinking about the future expansion or support for new and, I don't want to necessarily say better, but different index types for different use cases, and some of the ways that the work that you're doing enables that, and maybe some of the ways that people can experiment with those different index types without necessarily having to round trip it through getting it upstreamed into Lance.
We are not 100% of the way there that you can experiment without upstreaming yet without diving into the source code. But it's sort of like we are on, I think, our third pass now through indexing, like what abstractions we want to use internally to represent these vector indexes. And each pass, we're sort of narrowing down what those traits look like, what we need. And the reason we've done so many passes is because internally we've been having to experiment and play around with these different solutions. We had an HNSW solution. I think we still do. We have IVFPQ. So we're trying to come up with some good abstractions to finalize that. So I think we will get to a point where those abstractions are solid enough that you can turn it into a plugin at that point, an extension point. Today, if you wanted to, you'd have to kind of dive in and get a little bit more involved. But it's a fairly isolated part of the code base. So if someone wanted to do that and they shot us a message, we could get them pointed in the right direction. Scalar indices are actually a little bit easier. That abstraction's been pretty solid for a while. So we have been talking with some of the GeoJSON people. And I think at some point we might be able to do some integration there to see if we can build like a, I don't know what you call them, but like a quad tree GeoJSON type index to search geometry data, which would be pretty cool. And so there, like with the scalar index, we have two traits really. One is, here's a data fusion expression. Do you think this is something that you can search your index with? So you kind of have to parse that query. And then two is, okay, you parse the query into X. Now go tell me which rows match that.
And in your experience of working on Lance, working in this space of dealing with vectors and matrices as a storage layer, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
Yeah, I think cloud storage is always a lesson that I have never stopped learning. I joke with people that working with cloud storage, I very much feel less like an engineer and more like a physicist, where I have this unknown system and I just run experiments against it and I start to build up this model, and every now and then I'll run an experiment and it'll just shatter my model and I'll have to readjust and come up with a new hypothesis. And but I have a pretty good working view at this point of how cloud storage works, but it is constantly being just sort of like reinvented. It has gotten to the point now where I will find talks from like S3 people that went and talked at different conventions and try and glean information out of some of the random things that they say about like how they scale up their random access support. And for them, it's really IOPS per second support. So that's always a challenge. I've learned a lot about Parquet. I'm pretty sure I could write a Parquet implementation now. So that's been fun. I think this is more for me personally working at Lance. We've been able to work a lot with customers who are in this AI space, building these cool new AI things. And just, I guess this is, you asked for challenges. This isn't really a challenge as much as it's just a fun thing. Is that working with these customers and getting to see what they're building and turn that into realistic data engineering requirements has been a lot of fun.
And for people who are in the position of saying, I have a bunch of vectors that I need to store and work with, what are the cases where Lance is the wrong choice?
So I'll translate wrong choice into like, we're not there yet and we don't plan to get there soon. So definitely if you're doing like OLTP, Lance is not your application transactional database. We don't have support for multi-document transactions, and we probably won't soon. The other is if you're starting to do like TPCH, TPCDS style queries against trillions of rows, where you really want like a distributed query engine, we're probably not going to be tackling the distributed query engine TPCH scale factor 10,000 or whatever anytime soon. So we're more focused on the scale you can reach when you have images, which is surprising. But again, 50 billion, 100 billion, those are some of like our biggest targets there. And just like getting specific, like if you're working with the Lance file format or something versus Parquet, one thing Parquet does really well that we just don't have the resources to tackle yet is handling untrusted input. So you could be pretty confident if someone gives you a random file and you open it with Parquet CPP, then your worst thing's going to happen is you'll get an exception. If you open that with Lance, then you might have a panic and crash your whole process. So we haven't, if you're dealing with untrusted input or if you're dealing with, just files that you could have random garbage introduced, we haven't gotten there yet either. So I don't think we'll necessarily tackle some of these things, but if someone really was passionate about Lance and wanted to tackle one of these things, we would definitely help them go there.
And as you continue to build and iterate on and evolve the Lance format for file and table store of vectors, what are some of the things you have planned for the near to medium term, or any particular problems or problem areas you're excited to explore?
Yeah, we're working on a 2.1 Lance file format, which is not dramatically different, but it solves another problem that I really wanted to get to at some point, which is being able to do random access in either one or two IOPS, no matter what data type you have. So you could have 10 levels of list and struct indirection, and it still boils down to one or two IOPS. So that's fun. So better random access in general, we're always working on. Another kind of big new area that we're looking at is these training workflows. I mentioned when people need to access in random order some filtered set of their data so that they can feed their GPUs to train a new model. That's something that a lot of users we've run into have encountered. And it's something we do okay, but there's definitely room for improvement in how we solve that. It's sort of a perfect storm of terrible access patterns. And I think we've come up with some pretty good ideas for how we can do that efficiently. So that's coming down the hood. The other thing we've been working on is looking at just kind of database management, making it easier to scale up and grow your database, taking some of the tasks that you have to do manually today, like running compaction and re-updating your indices, and starting to make those things automatic and a little bit more foolproof.
Are there any other aspects of the Lance project, the format that you're building, or the applications of Lance to AI engineering or generalized vector and matrix search that we didn't discuss yet that you'd like to cover before we close out the show?
No, I think we covered things pretty well.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you and the other folks at LanceDB are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
So something I would love to, if all priorities went away and love to sit down and build someday, is I've had a lot of fun with the Substrate project. I think just like a lightweight, call it kind of vendor agnostic library for expressions, function expressions. It's like X is greater than 7 and 10 is greater than 5. You have like pair compute expressions. Polars has its own library for this. Data Fusion has its own library for this. Having something that's based just on Substrate and not really taking sides between the different implementations, but like a Python library would be nice and helpful. A fun project that I think would be tons of work, but if someone wants to build a open source cost-based optimization query planner, then go have at it. I think, again, we have these different query planners, like with InductDB, they have a really solid one, but it's not really exposed. Data Fusion has one that you can extend, but you got to let know about it. So it's one of those things that I think would help to have out there too.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing on Lance. It's definitely a very interesting project. It's great to see all of the work that's been going into it and the capabilities that it unlocks. So I appreciate all of the time and energy that you and the rest of the Lance team are putting into that. And I hope you enjoy the rest of your day.
Thanks. Had fun talking.
Thank you for listening, and don't forget to check out our other shows. Podcast.net covers the Python language, its community, and the innovative ways it is being used. And the AI Engineering Podcast is your guide to the fast-moving world of building AI systems. Visit the site to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story.
And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.